it? Here? Good. Okay, so my name is Stefano G. I work in Oxford under Bob Kuke, and I'm here to present some work that we did recently with a colleague on how to construct models that display what's known as higher order interference. So more interference than usually studied in quantum theory. So of course, as the panel discussed yesterday, there's a bunch of different ways that the word interference can be interpreted, and we mean a very specific notion here, i.e. we mean the interference from a two-slit or many-slit experiment. So you have particles, you have two slits, you send these particles through the slits, and what you observe is that even if you send them one at a time, so there's no way for a field, like an electromagnetic field, to interfere, you still get a distribution that is not what you would expect from the individual slits themselves. You get some, there's no antivirus for me. I'm not given an option to, you don't see that, but it's telling me that I can either renew Kaspersky or I can uninstall Kaspersky, which seems to be what I want to do right now.
You don't need it. Windows defend this.
Yeah, so what do I do?
Ignore it.
I can't ignore it. So, that's the, yes, Russian interference. It's a bad interference. So this is the kind of thing that we're talking about. We're talking about particles that individually behave in a way that's not expected from classical theory, and you can make an approximate model of this. You have some source that emits particles, electrons, photons, whatever you want. Electrons seem to be the thing because they are kind of mass-like, but it works with any quantum particle. You go through slits, some number of them, they hit the screen, and that's what you see when you do the experiment. But when you do the model, you don't want really to think about the details of this. You want the minimum possible model that describes the behavior, and that's, you have some state which describes the source, so it's the state of the particle before. You have some projection that happens by passing through some subset of the slits or all of the slits, and you have some measurement at the screen. And you want to see what the probabilities are and how they change depending on which subsets of slits you consider. So in the traditional two-slit experiment, you have essentially three options. You can either open slit 1, you can open slit 2, or you can open both. And then you study what the probabilities of hitting a certain fixed point of the screen are with the three combinations. Now, in general, you have some n-slit experiment, and the simplest model that you can have is to consider some orthonormal basis, so a subset of all the possible field states, which consists of those states that pass through a single slit with certainty. So you have these. This is the composition of your space. Of course, they're just approximating. In reality, they will not pass with certainty, but as long as they pass through a single slit with high enough accuracy, you're going to get your contradiction. And then you prepare your source in a uniform superposition. So your source will go through all slits with equal probability if they're open. And if you have some subset of the n slits which is open, that corresponds to projecting onto the corresponding basis vectors. So it will only keep the basis vectors, the basis states that pass through those slits with certainty, and all the others will be discarded. Of course, this is a linear setting, so it's actually not true. Every state will just be projected onto this subspace. And your screen can be any effect, because ultimately different points of the screen, different orientation of the screen will give you different practical measurements. But ultimately, all you want to see is that for some effect, you observe some interference, so you pick a convenient one. And the convenient effect is just the cat corresponding to your preparation. So what you see is you start with the state, goes through some slits, and then you measure and check what is the probability that the state remains unaltered. Now, you could work with the usual notation, but already when you start going into density matrices, you have these two-dimensional objects, and this talk will deal with 4-dimensional objects, so dealing with actual coordinates is really messy. So we introduced some graphical notation for this. Instead of indices, we're just going to use colors because that's a bit less notation heavy, and we're going to write down explicitly what the density matrices are. So cat, which is our preparation cat, corresponds to a certain state, and that state has 4 pieces, which are the 4 components of the density matrix. And similarly, the bra, corresponding to our effect, has 4 pieces, which are just the 4 components of the density matrix. Now, those are not all actual physical states. The 2 intermediate components, these 2, don't usually appear. But they are, so linear, they are just the off-diagonal components of the density matrix, and you can just treat them as vectors. Ultimately, density matrices are just vectors in some 4-dimensional space. And if you do that, then you can look at what the decomposition of the identity looks like. And the identity takes a density matrix and lets all of the components through unaltered. So it takes the top left component and lets it through on the top left, top right, lets it from the top right, and so on. So those are the 4 pieces that appear in the identity. Now, if you look at those pieces and you ask, okay, but what are the pieces that appear in projectors? Well, if you take a 2-dimensional projector, it looks exactly like that. It's just it's going to take the particle going through, the component going through slit 1 and pass it through, the component going through slit 2 and pass it through unaltered. So because we're going to use these components more and more, we just give them names, we color them, and we're going to have same color for the 2 dots or different colors for the 2 dots, so that we can just write our projectors in a simple way. And what happens is that when we compute probabilities, we're really just adding these pieces. We're counting how many there are. Because the component that goes through slit 1, so the diagonal component that goes through slit 1 passes through with this particular piece and doesn't pass through with other pieces. And each component passes through with its corresponding piece only. So calculating the probabilities in the interference experiment is just counting the number of pieces that appear in these projectors. So in the 2-dimensional projector, you get 4 pieces. Each piece is counting just once, because it's counted by the corresponding component of the state and the effect. We pick them to be the uniform superpositions exactly for this reason. All of the components in the density matrix have exactly the same weight. So we don't have to do any particular calculation. There's some proportionality factor in the beginning, we ignore it, we know what it is, and then everything appears just once. It's as if they were 1 and 0. But if we look at the projectors that go through 1 slit, they only have a single piece, because they only keep the top diagonal component or the bottom diagonal component, and they have zeros everywhere else. So ultimately, we can compute the probabilities really easily by just adding this number of pieces, and these probabilities don't satisfy the correct sum. So the probability of going through the 2 open slits and remaining in the same state is of course 1. You've done nothing to the state, you prepared it in a uniform superposition, it goes through, nothing happens. So you expect to measure it to be exactly the same state. But if you close one of the slits, the probability that you will get that state at the end is just 1/4 for each slit. And if you sum the 2, you get 1/2, which is not what you get by leaving both of them open. So this is already evidence. In fact, this is the only thing that you need to compute in order to show that there is second-order interference in quantum theory. That is the standard calculation. It comes from the fact that the Born rule is quadratic, but we don't want to look at that because it's hard to do the computation with quartics and higher orders. We want to think of it in terms of how many pieces do we have, do we count the pieces, does the sum coincide? And the answer in quantum theory is, of course not, because you have 4 pieces in the 2-dimensional projector and 1 piece in each of the 1-dimensional projectors. So you have 4 non-zero entries in the resulting density matrix for the 2-dimensional projector, and you have a single non-zero entry in each of the 1-dimensional projectors. Now you can generalize this, and if you have some arbitrary number of slits, all you have to do to compute the probability is you compute the number of pieces, and multiply it, you normalize it by 1 over n squared. And this gives you that there are 4 pieces in 2-dimensional projectors. There's 1 piece in each of the 1-dimensional projectors. And interference is just the observation that 4 is greater than 1 plus 1. Really. But this is all just a reformulation, if you wish, of what you already know about interference in quantum theory. It's nothing new. This is not surprising, because you can reformulate this in terms of the usual Bohr rule. You can write it in terms of inner products. It gives you always the same result. But it helps to generalize this to higher order. So what I'm interested in is something even more basic than counting the pieces, which is the observation that the shapes of the pieces are different. So if you have a single color, so if you have a single slit open, then you have only one possible shape. Your pieces can only be both slit 1 or both slit 2. So your projector only keeps either the top diagonal component or the bottom diagonal component, nothing else. So both indices of the density matrix that are kept are the same. Either it's the 1, 1 component or the 2, 2 component. But if you have at least 2 colors, then you have more possibilities. You have these off-diagonal elements which have a different shape. The 2 index values for the component are different now. So you have these the off-diagonal components that get available. And the observation is essentially that a new shape appears, so the 1-dimensional projectors cannot give you everything, simply because there's not enough shapes. They don't have all the shapes available. But what happens is that if you have 3 or 4 colors, at this point nothing happens. Because density matrices are 2-dimensional objects, you only have 2 possible indices, and so you only have 2 possible values. If you have 3 available values, you don't get anything more, you're just going to get more combinations, but the shape is always just either diagonal or off-diagonal. There's nothing else. So you have no new shapes, and in fact, this turns out to imply that there is no higher order interference in quantum theory. And again, this is something that you already know, so I'm not really telling you anything new. But what I am trying to prepare for is the statement that second-order interference is a quantum thing. So if you sum the 1-dimensional projectors, you don't get everything you need. In quantum theory, there's no higher-order interference, so you satisfy that inclusion-exclusion formula at level 2. But in other theories, you might be able to obtain interference of higher order, where that equality is also violated, and the equality for level 3 is violated, and the equality for level 4 is violated, for example, or depending on what your theory is. Now, there's some work that suggests that this should not be possible under certain assumptions. In the last couple of years, there's been a few no-go theorems. There's been renewed interest in the study of this particular feature. Well, as it turns out, the no-go theorems leave enough room for maneuver that one can construct infinitely many models where higher order interference appears, and it is as high as you want. So I'm going to go to the second part of the talk and show you how to construct one such model, so the easiest one that you can construct. Now, the observation is that the Bohr rule secretly comes from a symmetry. Secretly, you have the complex numbers and this conjugation symmetry on the complex numbers, and you can think of this as a group symmetry. It's a Z2 symmetry. You have either the identity of the complex numbers that leaves things unaltered, or you have the conjugation on the complex numbers, which is an evolution. So you do it twice, you go back. This is just a group theoretic thing, and there's a decent amount of mathematics about this kind of constructions. They're known as Galois field extensions, or finite order Galois field extensions. And this particular one is the one that constructs the complex numbers from the real numbers. You've added the root of -1, so if you invert the 2 possible choices for the root of -1, you get this conjugation symmetry. That's all that you're doing, really. You're commuting the roots of certain things. Now, from this symmetry, you get a norm, which is the usual norm, and you can extend this norm to Hilbert spaces, and this gives you the usual trace norm on pure states. So the trace norm on pure states comes from this, and it's not too surprising because ultimately this is an inner product norm. So you can think of it as an inner product, but I strongly suggest, at least for the rest of this talk, that you think of it as coming from that particular symmetry. Because those n that you see are nothing but the Galois norms. So this is a well-studied thing in algebra. The fact that it coincides with the inner product norm is not entirely an accident, but partially an accident. And you get the Born rule from the same very norm. The Born rule has nothing to do with the inner product in this particular context. It's that you pick the symmetry on your on the field that gives you your amplitudes, and that symmetry just snowballs through, and you get the Born rule out of it. So the idea is, if you change this symmetry, then you will get a different Born rule, and it's one that will be well defined and that will behave nicely with measurements and will give you potentially some interesting new results. So that's what we did. We moved from matrices, which are two-dimensional, to hypercubes, tesseracts to be precise, which are four-dimensional. And we took the usual conjugation symmetry and we turned it into Z2 cross Z2 symmetry. So we conjugate twice. We conjugate in a horizontal direction, we conjugate in vertical direction, and in diagonal direction you get nothing because the two conjugations cancel out. Now this seems really straightforward and it's very simple, and you might expect that nothing really comes out of it, but from a two-dimensional object you get a four-dimensional object. From a quadratic norm on your complex numbers you get a quartic norm on your complex numbers, and from a quadratic Born rule you get a quartic norm. So in fact, something might happen. There is a possibility that because you go from quadratic to quartic, even though they look really similar, you will get some higher order interference. And the easiest way to see this is to look at the kind of shapes that you get from this new object. Originally you only had 2 points, so the possible shapes were the 2 points with different values or the 2 points with the same value. And now we get a lot more combinations, because you now have all 4 points with the same value. You have all possible ways of assigning 2 values to the 4 points. You have possible ways of assigning 3 different values now and 4 different values. So from these new shapes that have emerged because your objects are now 4-dimensional, you get that different numbers of slits are necessary to get pieces of different shapes. So you get with one slit you only get the shape where everything has the same index value, all coordinates have the same index value, that's the diagonal. And if you have 2 slits, you get some off diagonal elements. But the problem is that now the diagonal is not in a 2-dimensional object, but it's a 4-dimensional object. So there's different notions of what off diagonal means. And it's kind of hard to see just with the algebra whether they're all covered or not. But if you draw the pictures, it's really easy. Those shapes of off-diagonal elements can be obtained with 2 different indices, but not all of them can. There's a bunch more that can't. So from this argument, if you believe that ultimately interference is a matter of shapes, you should already see that in this particular model you expect 3rd-order interference and 4th-order interference, but not 5th-order interference, because once you have at least 4 distinct values, you don't get anything more. You have 5, nothing happens. You have 6, nothing happens. And that's exactly what happens. 2 slits are no longer enough in this case, so you do get 3rd and 4th-order interference. And the reason is that you can just use the formula. The probability is still a renormalized version of the number of pieces in your projector. And now you can just write down the combinatoric expression for the number of pieces in your projector. And those are the not so ugly numbers, to be fair. I expected them to be a lot worse, and those are correct. It's just K is really the number of pieces. It's just writing hashtag U every time was ugly and not really. And then if you don't believe the argument about the shapes, you can just compute. You count how many pieces there are in 3-dimensional projectors, you count how many pieces there are in 2- and 1-dimensional projectors, you apply the inclusion-exclusion law, and you don't get an inequality. You get an inequality for 3-dimensional projectors, which shows that there's 3rd-order interference in this model. And if you do the same with 4-dimensional projectors, you get a slightly longer formula, which doesn't fit in half the slide any longer, and you get a slightly longer calculation, and again you get an inequality. So you know that you have 4th-order interference. You don't expect to have 5th-order interference, and if you do the calculation for 5, you get an exact equality. And from there on, you know for certain, because there's a theorem that states this, that there's not going to be interference of any kind. So by going from a 2-dimensional object, the density matrices, to a 4-dimensional object, so by changing your Born rule from a 2-element symmetry to a 4-element symmetry, you get 4th-order interference. And in fact, this works for arbitrarily high orders and arbitrarily leading groups. So you get all sorts of numbers in different combinations. That's just the symmetry of the object that you're dealing with. And just to conclude, I wanted to mention that because there's been some talking about these semi-ring matrices, these are all essentially exotic models of quantum theories that have been studied and that give a bunch of interesting features. What's important is that this particular construction works for all of them. Instead of having the automorphins of the complex numbers, so instead of having only the conjugation essentially, because that's the only thing that you can do to the complex numbers, you have all the possible automorphins of whatever semi-ring you work with. So the Booleans are very trivial, but finite fields are really interesting. So if you do something with finite fields, then you get a lot of these possible constructions, and they're all distinct. And your new norm is the Galois norm. You construct it from the symmetry. It's a completely generic thing that you can reason about, and you get probabilities out of this. Your Born rule is now given by this more general Galois norm, and you can construct arbitrary models, except that you have to leave the probabilities behind. So your notion of non-determinism is not naturally the real numbers. It's something else. Sometimes it's going to be something familiar. For example, you could have the signed reals, so you have these quasi-probabilities or the signed probabilities, as people call them. They have been studied well. Sometimes you get the Boolean numbers, which are possibilities, and they've also been studied, but sometimes you get some more exotic objects. Like you get finite fields as values for your probabilities, or the p-adic numbers as values for your probabilities, which have also been studied, are also of interest, but of course they have their own issues, and they're not probabilities in the usual sense. I wanted to mention that a lot of these models have actually been studied in the context of quantum theory, so interference has been in one way or the other studied in these. It's a bit smaller than I expected it. So there's the complex case, which is the usual quantum theory, but then there's the real quantum theory, there's the Booleans, which is relational quantum theory, or the REL model, which is very well studied in the context of categorical quantum mechanics. There's other things. There's modal quantum theories constructing finite fields. There's hyperbolic quantum theory, which is just split complex numbers. If you don't know what those are, you just take the root of -1, and instead you take the root of +1. You add a new root of +1, and things get really different, and you get something which is interesting in terms of relativity. And you have p-adic quantum theory, which has been studied, and you can study tropical quantum theories with the tropical semi-rings, for example, and you get some exotic models that resemble the relational ones. And all of these things can be used to stress test these constructions, and all of these things support both second order and higher order interference. So you can do this arbitrarily high Born rules with all these possible choices. There's a large landscape of models that you can study, or you can use to construct models of meaning with weird semi-rings, or you can use to try and understand how quantum theory works. And this is really interesting, and I've spent a decent amount of my, in fact, probably almost the entire amount of my PhD doing these things, and it was fun. And what you get out of it is that you understand interference in a very different way, but you also understand non-locality in a very different way. You can study what non-locality means and whether the arguments go true, and some of them, for example, the Mervin ones, go true in a lot of these models. You can study whether there's computational speed up in these models, and it's known that in some of them, in fact most of them, there is some form of computational speed up, at least in some of the problems. And you can study dynamics in these models, and they don't look necessarily like the usual dynamics, because lots of these models don't have a differential structure on them, but they have the same operational features and very similar algebraic features. So all of these things are of interest, practical interest, and they give you stress tests for what quantum theory is, what it means, and how it can be applied in different contexts. So with that, I will conclude. I have little conception of what time it is, but if you have any questions,